the book, starts at the bottom of page 173 and takes pretty much the entirety of page 174, and is very, very challenging to follow, and you know what I mean if you try. Okay? And I think everybody should try. You should try to understand it. Okay? It will deepen your understanding of details even if you don't quite see, or you can't imagine doing that proof on your own. That's a pretty tough proof. I do have another animation here. Ah, yeah. This illustrates the summation board. For each subinterval in the partition, the heights of these orange rectangles represent the oscillations of the function over these different intervals. And the widths are the delta x's. By making the partition fine enough, making all the delta x's small enough, you can make the sum of the orange areas as small as you like. This makes it more believable, right? Look at that. Each of those orange rectangles is very small, and in fact, the sum of their areas is very small. It can be made as small as you like by choosing the number of rectangles sufficiently large. Doesn't really matter what the function is here. You can still make the sum of those orange areas as small as you like. Okay, so that at least makes this fact believable when you look at a picture like that. Are there any proofs you should be able to do from section 5.1? Well, I mentioned you should be able to prove that a piecewise constant function with two separate pieces is Riemann integrable over the interval you're thinking about. That's probably the hardest possible proof, but I have put it on exams before.
So like when we finished up with class?
Yeah, on Friday, yep. So you should practice proofs like that. It's possible I might give you a little guidance in the problem description. Remind you of what to do, but you should practice enough that you don't need that guidance. So it's hard proof, but it's possible in the test. Another possibility would be to prove, well, for example, the linearity property of definite integrals. I'll just write it as an equation, but of course it would have hypotheses. The hypotheses would be, suppose you got two functions f and g defined in a closed interval from a to b, and suppose f and g are Riemann integrable on the interval from a to b. The conclusion would be f plus g is Riemann integrable on that same interval, and the integral of f plus g equals the sum of the integrals of f and g. Should I say that again? The assumptions, and you can look in the book. You've got two functions, f and g, defined in a closed interval, assumed to be Riemann integrable on that closed interval. The conclusion would be that f plus g is also Riemann integrable, and its integral equals the sum of the integrals of the two functions.
Whenever there's theorems in our books that you say we should prove, but the proofs are not in the book, what do you suggest us to do if we can't seem to come up with?
Well, some of them do have proofs in the book, and others are exercises. Like this is an exercise that you had. That was one of the completion problems.
Okay.
So, or else try to figure it out. Yes, if it's not super hard. This one's tricky enough. I did make it a completion problem, so you should think about it and study it. Let's think about the scratch work here. Not a complete proof. You need to think about Riemann sums for f plus g. Can such a Riemann sum be made as close as you like to this? That's really the issue. You want to make this quantity with smaller than any given epsilon by taking the norm of the tag partition sufficiently small. Somehow you've got to use the Riemann integrability of f and g. Does anything pop out to you as far as how to use that? I do see these individual integrals here. Maybe this notation makes it less clear. This is a summation, really. It's just notation for a summation. This summation. Does that help make it more clear what to do?
Break them apart.
Yeah, break it apart. That summation can be broken apart into two separate summations that look like this. Is that obvious? Technically it is if you know properties of summations. If you had to justify that from scratch, technically speaking, it's part distributive property, and it's also the commutative property. After you use the distributive property, here you get a summation like this. I'll write it out without summation notation. I'm not going to bother writing the last one. It's a finite sum. To get from here to here, it's a matter of rearranging things, grouping all the f's together, and grouping all the g terms together. That's the commutative property for addition. Would I make you say that? No. But you should know this summation does equal this, the sum of these two summations. And that helps you finish the proof, because then you can say this equals, I'll go back to the S notation. It equals that. Then what fact do you think you'll need? What real fundamental fact from chapter 1 would come next?
Triangle inequality.
Triangle inequality, yeah. This is going to be less than or equal to this. The absolute value of this difference plus the absolute value of the other difference. That's the triangle inequality. We never go away from using the triangle inequality in this class. It's always there in the background, always needed for something in each individual chapter. So, I want to stop the scratch work here and just think about how you do the proof. You might want to write what I say. In the proof, you'd say let epsilon greater than 0 be given. You want to choose a delta so that something happens. Well, you can choose a delta 1. Since f is Riemann integrable, such that if your tag partition has norm less than delta 1, this distance is less than epsilon over 2, say. And you can choose a delta 2. So if the norm of your tag partition is less than delta 2, this difference is an absolute value less than epsilon over 2. What do you think delta should be? If you've got a delta 1 to make this true and a delta 2 to make that true, minimum, yeah. Your delta will be the min of delta 1 and delta 2. not the inf. It's important that that's not an inf, although it equals the min in this case. You've got a finite number of numbers in here. The inf will equal the min. This will be a positive number. If you had an infinite list of positive numbers and you were taking their inf, it might not be positive. It could be 0. So it is important that there's a finite number of these. You can say inf or min, the same thing here. It will be a positive number. Then say, suppose you've got a tag partition with norm less than that. Then both of these would be less than epsilon over 2, and you'd be able to say, oh, this is less than epsilon. So that's a proof. It's not too hard. Not too hard. I mean, it's not. I'm not saying it's easy. It's exam level kind of problem. Maybe that's the best way to put it. It's not easy, but it's not hard. It's somewhere in between. It's an exam level kind of problem. The proof that if f of x is less than or equal to g of x for all x in the interval, leading to the conclusion that the integral of f is less than or equal to the integral of g, and these are assumed to be integrable functions. That proof's a bit trickier. It is a completion problem proof. You do have access to the key. It's a bit trickier. I did it by contradiction. Maybe too tricky to put on the test unless I gave you a big hint. But I think still worth studying. You should be able to, of course, state the definition of Riemann integrability. And I think if I had you state it, which I probably will, I think it's typically on this exam. I think in the past I've sometimes had people define what a tag partition is and what a Riemann sum is, but perhaps I would say, assume you know what a tag partition is and what a Riemann sum is. And then state that definition in terms of those things. And I don't know, I think, I probably will put that definition on the test, and I think I'm feeling a vibe from myself, from my soul, that I don't want you to have to bother saying what a tag partition is and what a Riemann sum is. Just know what those are. All right, going backwards, chapter 4. Section 4.3. You should certainly know the fact that derivatives satisfy the intermediate value property. It's not a name theorem, so I don't think I'd have you state it, but if it came up in a true-false question, you should know the fact. I said you should study the proof, and it's not a super hard proof, but it is kind of tricky. It does involve a trick. I'm looking at page 147 and 148. I don't know, I don't think I've ever put it on a test before. I don't think I'm going to put it on your test. I mean, it's still worth studying a little bit to understand it and see that the extreme value theorem is actually necessary. So it is based on the completeness axiom as well, because the extreme value theorem required the completeness axiom. You should know the definition of concave up and concave down, and again, sort of the odd cases you should know, for example, technically speaking, according to this definition, a straight line, whether its slope is 0 or not, is both concave up and concave down, according to this definition. That f prime increasing means f prime could be constant. F prime decreasing means f prime could be constant as well. And the fact, could come up as a true-false question. If f is twice indifferentiable, then f is concave up on the interval if and only if f double prime is non-negative. And a corresponding fact, it would be concave down on the interval if and only if f double prime is non-positive. Non-negative means greater than or equal to 0. Non-positive means less than or equal to 0. So mostly it's just, I think in that section, knowledge of facts, essentially. Certainly I think I probably can't resist putting a proof on the test where you will either prove the mean value theorem or use the mean value theorem in a proof, or use Rolle's theorem or use the monotonicity theorem in a proof. We did quite a number of examples of those kinds of proofs. We talked about the proof of the mean value theorem. What else did we do? We proved, or we at least mentioned how to prove that antiderivatives of the same function differ by a constant on a given interval if they are antiderivatives of the same function on that interval. The proof can be proved with what I call the constant function theorem. That if the derivative of a function is always 0 on the interval, then the function is constant. We also proved that what else? We proved that e to the bx actually a times e to the bx was a general solution of a differential equation. Y prime equals by was the differential equation. That means both that this function is a solution of the differential equation, its derivative is b times itself by the chain rule, and that any solution of the equation is of this form. That was the more important, more difficult thing, I guess I should say. And we did it with a trick. Assuming g is a solution, we showed that the derivative of that function was always 0, and therefore by the constant function theorem it was always a constant. And that meant that g of x must be that constant times e to the bx. We call the constant a. Solving for g of x, you see g of x must be in this form. Other kinds of problems I've given on tests that are kind of similar to this is actually related to solutions of second order differential equations. I have given problems like that. Here's a type I've given in the past. Assuming you got two functions, f and g, that satisfy the conditions that f prime equals g and g prime equals negative f. We didn't go over a problem like this in class, but I'm kind of going over one now. This is the kind of problem I've given before. Assume this is true for all x, which does mean, by the way, that f and g both satisfy a certain second order differential equation. If you take the second derivative of f, you get the opposite of f, and the same with the second derivative of g.
Can you explain what a differential equation is if we haven't taken the class?
Well, I explained it when we talked about this. I'm also explaining it just by saying that the second derivative of this function equals the opposite of itself. That's an example of a differential equation. It's usually written in this notation. If a function satisfies this kind of equation, if you write it in Leibniz notation, it's typically you call it a differential equation. It's an equation involving derivatives of an unknown function. We don't know what f is here. G is going to satisfy a similar differential equation. G double prime will also equal the opposite of itself. And I've also often said, okay, I mean, you can do this without knowing about differential equations. I could say, just assume this is true. That this is true and this is true for all x. Make that assumption. Okay? You don't have to know about differential equations. And the conclusion I might ask you to prove is, amazingly, f of x squared plus g of x squared is a constant. What do you think f and g might be? Sine and cosine perhaps, or maybe multiples of sine and cosine. Second derivative of sine is the negative sine. Second derivative of cosine is negative cosine. It could be 2 sine x and 2 cosine x as well. But you don't need to know about differential equations to prove this. Use the constant function theorem. Try to show a function's constant. Differentiate this thing. Show its derivative is always 0. You must have to use your assumptions. You'd be done. Pretty quickly. It's a pretty quick proof when you use the constant function theorem. And yeah, you don't need to know about differential equations to do this. I'm just giving that as background information. I've given a problem like that, I think, on past real analysis exams too, though I'm not absolutely positive that it's on any one of the ones that are on Moodle. But you can look and see it. If there is a problem like that or not. What else? Those inequalities, come back up to the screen here. I've sometimes put on tests. Like this one. And I hinted at a more general fact. In fact, I think I did write it on the board. It's also true that this says the cube root of 1 plus x is less than 1 plus x over 3 for all positive x. You could also say the fourth root of 1 plus x is less than 1 plus x over 4 for all positive x. And the fifth root of 1 plus x is less than 1 plus x over 5 for all positive x. These are all true facts that can be proved with the mean value theorem. I have sometimes put proofs like these on old tests, and they could be on your test. We also proved that fact about the sine function, this fact, using the mean value theorem. I could put the proof of the first derivative test on the exam.
Was that completion?
It might have been, I forget. Was it? Okay. You actually don't need to use the mean value theorem. You could, I could say use the mean value theorem for that. Though that would be a little more work than you might want. It'd be quicker to use the monotonicity theorem to prove the first derivative test. You do need to know the definition of a local max or min, relative max or min, which is back in chapter 1 as well. Theorem 4.10, page 139, is technically a named theorem. That's Fermat's theorem. So there's a couple theorems, I think 2, since in chapters 3, 4, and the beginning of chapter 5, that I've given names to, but the book has not. One is Fermat's theorem, theorem 4.10, page 139, that says if you've got a function that has a relative extreme value at a point C that's not an endpoint of the interval, then C is either place where f prime equals 0 or f is not differentiable at C.